We're now recording. I will do the same thing as I did for the first class. Give you access to the recording. I think I'll make this YouTube so I can add the captions and all those other fancy things. Okay, let's see. Where do we start? First, hello everybody, and second, let me open here. This one too. I'm Today at least I have my tablet, which is an improvement this time. So we'll um, work as if we had a blackboard. And that's for the ones that already know, that don't already know me. That's what we're going to do during the semester. I'm going to write on a tablet, and um, then I'll post the PDF. And the first one was pretty much empty. You have it on Canvas already. Please check Canvas. I'll do announcement. I'll try to run everything through Canvas so that I know where things are. If there is anything related to the course, and you also know where things are under the same condition. Let me also put my phone and do not disturb, which I forgot to do. In general, in class, I will hope everybody to do the same. Is there somebody that's not muted? Sure. Anyway, if you need to speak, I guess just speak up. If as we would in class, there's few enough of us that should not be a problem. If you're not speaking, please keep yourself muted just in case. Um, all right, so let's start talking a little about um, the first topic we're going to discuss in our course, which is what is called numerical root finding. Let's see, second, and it's probably best if I share here. No, no, what's happening? Okay, let's see what it is. All right, technical problems. We're getting there. Should be able to. Perfect. See my screen now. Very good. Okay. So what that means is that we're going to look for solutions of an equation where the solution cannot be found analytically. Well, in principle, you can also do it if you, for whatever reason you want to do it, even if you know how to find the analytical solution, you can also still do it numerically. There is no, there's nothing stopping you from doing that. So this thing has a bunch of different plans. Last semester, some of you were with me, and I was asked to use a darker, thicker one. That would be the black one. I like writing in blue. Any preference? Doing to make a vote?
I like the black personally, the thicker
Black,
black one.
I like the black as well.
black. Anybody speaking up for blue? No, just not in a blue mood. Okay, let's go black. Thanks. All right. So what we're going to do is find the solution of f of x equals 0. I'm not giving you any examples, but this actually is less useless than you may initially think. Um, you can use this for doing various things. For instance, if you want to calculate a number like square root of 2, and there is a lot of ways to do it, actually. This is an easy one. But one way to do it is to solve the equation x squared equal 2. So if you have an efficient way to solve that equation, you have an efficient way to calculate square root of 2. I'm actually going to ask you to think of examples in physics when you can do this. But um, for now, take my word if you can think of anything on the spot that this actually happens. Okay, so the first um, take at this problem is going to be the one-dimensional one, which is sorry, which is in fact what you encounter pretty often. Fortunately, two-dimensional ones are harder. But by one-dimensional, I mean that I can do something like this, and here I have f of x. Here I have x, and f of x goes like this, and I want to find this magic point, x0, where f of x equal to 0. In principle, f could be, in more complicated problems, could be a vector, and it could be a function of x and y and z and so on. So that's a much harder problem. So let's start with this one. Um, there are essentially two approaches, I would say, for to doing this, and they oops, sorry, I'm jumping ahead of myself. Okay, that's not how you spell root, apparently, and depend on whether when you know what. It looks like the syncing is a little slow because I'm typing on, I don't see it on the screen yet. So one thing we can do for a function like this one is f of x is what is called bracketing. That is, find two values of x, let's call them x1 and x2, such that f of x1 is, let's say, negative, and f of x2 is positive, and then I'm going to expect that um, the function is going to have a 0 between x1 and 2. I'm going to put all these pieces together and say, well, but then if that's the case, um, let's just for convenience assume that x1 is less than x2, or let me just write it this way. X0 is in the interval. That's going to be an open interval. It doesn't really make any difference. As you've already seen, a little here. Um, since we're dealing with numerics, math is not as exact as in uh, courses in the math department. So, that means that numbers are not exact numbers. We may get a good approximation of of whatever number, but where chances are we're not going to have an exact value for a number. That's what we want. Um, and it's not going to make a lot of difference if we include or exclude um, extremes from intervals and so on. Okay. Um, so we may decide to start our search for the point x naught for a couple of points x1 and x2, where we know that the function changes sign between x1 and x2. How do you find those 2 points? That's another issue. And that's going to be a little problem dependent. There's a lot that goes into it. The other option is to say, well, I'm just going to start with 2 points, even if they are the same sign, or I'm going to start with one single point and take it from there. Um, if we start with 2 points with a bracketed root, uh, the two ideas I can um, um, give you are one, take your function, evaluate it in a bunch of points, and hope it changes sign somewhere. So that's kind of brute force. If you don't have any better idea, if it's a physics problem, you may have some ideas. Say, for instance, you're looking for um, some mass that will make some equation be satisfied. Okay, you know that's going to be positive, so it's going to be between 0 and infinity. And if you're in uh, you're working on a celestial body, you know what the mass is going to be less than the mass of the sun if I'm in the solar system, most likely. So whatever. I'm just making up an example, a silly example, but the point is, let the physics guide you on how to choose your starting point. Now, our first option for root bracketing. So if I do root bracketing, this thing stops. Argue with me. Thank you. I have to write on here. Is an algorithm that's called bisection. And here is how it works. So I'm going to make a sequence of points with the idea that each new point is getting me closer to the actual solution. So the point x0 I'm looking for. So I start with x1 and x2, knowing that f of x1 times f of x2 is negative. That means one of them is positive, the other is negative. Uh, Typically, for illustration purposes, I'm going to assume that x1 is f of x1 is negative, but it doesn't really matter. I can always also change the names between x1 and x2. Okay, point x3 is going to be given by this expression. Then I check f of x3, and you can probably see what happens. So I'm right here, so this starts working. Okay, so if can write it in different ways, but let's say just for simplicity, f of x1 times f of x3 is less than 0, that means that f of x1 and f of x3 have the opposite sign. That means that f of x3 has the same sign as f of x2. Then um, I'm going to replace x1 with x2. Um, sorry. Well, I'm going to replace x2 I don't know if it's appearing on the screen yet. With X3. Very straightforward. Otherwise, I'll do the opposite. That is, I'm going to replace X1 with X3. And this is not appearing yet. I'm typing it will appear momentarily, hopefully. Um, so then I'm saying, well, I'm going to change name to X3 and I'm going to call it either X1 or X2. And I'm just going to repeat this step as many times as I need to find a good enough approximation of the zero. Uh, Binary search. I do not know how to answer the question. I don't know what the I don't know what the binary search is. Um, I may have to find out and answer the question next time. All right, next time. I'll tell you later. Next time is still going to be unpleasant, well, less than ideal class, but then hopefully will be done for a good number of weeks. I have doctor appointment was scheduled 6 months ago, Tuesday, and I don't want to move it another 6 months. So I will do the same thing as I did with the first class. I'll try to record something. Could be um, something aside or a little aside, or maybe continuing this discussion depending on how far we get today. And I'm sorry that we get to through 3 classes without meeting in person, but at least we're not losing all of these classes. That would be a much bigger issue. Okay, so it's clear how this works. Um, let's see. Let's look at an example. So I need to stop sharing. I just start sharing from here. Um, this way. Okay. Yeah, make this a little bigger. So here I have a bunch of functions. I'm just going to use them as example. And here I'm going to show you how this goes. Um, before I go through, there's one more point. First, some of you contacted me saying that you have no experience with programming. I think that um, the crash course on MATLAB that is on the MATLAB website should be enough to get you started through this course, and then you'll learn what you need um, as we proceed. If if that is a problem, yeah, I mean, if that's not good enough, let me know. And if it's good enough, also let me know, so I do know that it's good enough. But going back to what we just wrote, this is sort of a logical construct that we can turn into a code. Um, I have here at the beginning, I need some initial data, and then I have an algorithm for calculating the next one. So all of this thing is going to be um, in some type of loop. Could be a for loop, a do loop, depending on the language you're using, can be written in using different keywords, but the logic is always the same. In the program, you can write a set of instructions and then tell the program keep doing the same thing until this condition occurs. And the condition could be do it 100 times, so until you've counted to 100, or the condition could be until the the error is small enough, or I find the exact solution. In fact, you may have noticed that in my little code here, I've not included the option, what if f of x3 is exactly 0? That just doesn't happen. It's not even worth worrying about putting it in the code. In principle, it could happen, but I'm um, so I'm working again with inexact. I don't know if that's an official word, but that's how I think of it, with inexact mathematics, meaning I'm not going to be able to represent any real number exactly. In fact, not even a rational number. Well, in general. So um, I'm going to assume that the root of my function is some real number, and I'm just going to expect I'm not going to be able to represent it exactly. So I'm never going to find it. But I'm going to be able to get as close as I like within the capability of my code. So the condition for stopping in a loop like this will be something like when x1 and x2 are closer than a certain value, that means I know the value of x0 within that approximation. I know that x0 is between 1.001 and 1.002. Um, the other option would be to say when um, the absolute value of x1 and, sorry, of f x1 and f x2, the absolute values are small enough. Um, the There is value to either option. You have to be mindful though, of the problem you're working with. So I gave you the example, silly example. I'm trying to find the mass of some celestial body, whatever, and I'm going to write it in kilograms. Okay, I'm not going to find want a difference between x1 and x2 that is 0.001 kilograms, because this celestial body is going to be, uh, I don't know, mass of an asteroid. I don't know what it is. Some of you may know, but it's going to be too many digits. It doesn't really get me anything to find that many digits of accuracy. So that what you have to be considering is how how the numbers in your problem look like, and how accurate you need the solution to be. Because if you um, if an accuracy of 1% on the value of x of x0 is good enough for your problem, there is no reason to keep going. Well, after you've reached 1%. So those are all things to keep in mind, and you'll see them in uh, some example. Now, I've got this written in Mathematica instead of MATLAB. Um, I hope that's not confusing, but this to, in part, to show the the logical programming is the same regardless of the language you use, and what's going to change are a little bit the instructions. Okay, so here I'm doing a bisection root search for the function f4. Let's go back and see. This is x squared minus 2. So I'm going to try to calculate the square root of 2 by solving x squared minus 2 equals 0. Oh, incidentally, you may have some function, um, and you're trying to find the value of x for which that function is equal to some value that's not 0. Just take the right-hand side, move it to the left-hand side, and you have a new function g that is going to be equal to 0, the value of the x that you were looking for your other function. So this is completely general. If you are looking for a solution of f of x equal to a different number, just take the different number to the left-hand side, and then you have new f equals 0, and this all applies. Okay, let's see what I'm doing here. I'm starting from between 1 and 2. Sorry, my two guesses are 1 and 2. I know that in this case it's easy. I'm using square root of 2. So I'm looking for square root of 2, and this is my function. And I see that if x is equal to 1, the function is equal to minus 1, so it's negative. X is equal to 2, the function is equal to 4 minus 2 plus 2 is positive. I've bracketed the root. And now I can do a bisection. So here in my code, I assign the two values of x. I calculate the values of the function. I'm just going to call them y. And here I'm making a um, just a table with values, and I'm going to fill it with numbers as I proceed. And you can do something very similar in MATLAB. Just the language is a little different, but the same logic applies. I can build a matrix and put numbers in, and then the reason why I put numbers in is that I can look at them at the end. Okay, so x3 is going to be equal to x1 plus x2 divided by 2, as promised. I calculate y3, and then let's do this product. If this is positive, that means that y1 and y3 have the same sign. They could be both negative or both positive, doesn't matter. So if they have the same sign, I replace x1 with x3. Now the root is going to be between x3 and x2. Otherwise, y2 and y3 have the same sign, I do the opposite. And then I save my number for my iteration, and I proceed to the next number. So this is the instruction that says the index I goes from 1 to this maximum number. I started from 1, now the index is going to be equal to 2, and I repeat this calculation. Everything clear about how I'm doing it? Okay. And then I'm also going to tell Mathematica, use your find route, so the built-in algorithm that finds the value. I could do it, I know that the answer is square root of 2, so I can just tell Mathematica, calculate the square root of 2. But this code I can use in general. So this is going to give me, in general, but not always, a very good approximation to the root. And then I can compare what I did with what um, the very clever algorithm that is hidden here did, and see how well it went. All right, so here's my table. So this is my starting point. What is the value of x1, value of x2, and the value of the function in those 2 points? See, I'm very far from well, um, I'll call this very far from 0. Again, that depends on the type of problem you're solving. So my next iteration, 2 becomes 1.5. So I do 1 plus 2 is 3, divided by 2, get 1.5. The function, my function for 1.5 is positive, so I keep the 1 and the 1.5, and I see that here I went from 2 to 0.25. Next iteration, get 1.25, and little by little, these two numbers get closer to 0 on both sides, and these values get closer to the actual square root of 2, which is kind of this number here. But you see that after 10 iterations, so it's not too bad. Well, I guess a matter of taste, but I got the first 3 digits, 1.41, correct. One, oh, sorry, one of the two values for because the fourth digit correct as well, the other one not yet, but in another iteration or two, I will get that correct as well. And then you keep going. Don't mind the language here. All I'm doing is plotting the okay, what is it I'm plotting? Yes, okay. So this is the value of the function, and this is the points. So the value of the function, the two values of the function, get closer and closer to this value, which is 1.4414, and so on. And the other value is the numerical values of x1 and x2. Sorry, these are the one on top is x1 and x2, and the one at the bottom is the value of the function. Ooh. Unfortunately, these two both start with 2, so I got self twisted. But this is the value of x, and this is the value of the function. We should go to 0. Everything clear here?
Luca, in your table that you showed up earlier above the last two columns on the right, what are those again?
Those are the values of the function. So f of x
Okay. Yep.
calculated in x1 and in x2. So they should both go to 0 or get closer and closer to 0. And in fact, you can see
Yep.
that they're started from numbers of order 1, now they're 10 to minus 3, 10 to minus 4.
Okay. Got it. Thank you.
Okay, any other questions? All right. Now, the I can give you some good news and some bad news. Um, I'll I usually start from the bad news, but I'll give you the good news first. If the uh, assumptions, all the necessary assumptions are satisfied, this method cannot fail. This is guaranteed to work. There is no fooling it. It's going to find a solution, and it's going to find a correct solution. The the bad news, there's two sets of bad news. One is I haven't really told you what the assumptions are. I kind of cheated a little bit intentionally. I want to emphasize the point of what can go wrong. But the one assumption is that you need to bracket the root to start with. And there is another assumption that is going to be obvious after we conveniently forget it, which I'm going to show you in a moment. The other bad news is that in terms of how quickly we're going to get to the correct solution, this isn't very good. And there are methods that can get close to the correct solution much faster than this one. And this may or may not be a problem if the if evaluating evaluating the function is not expensive, like I did here, x squared minus 2 was my function. It doesn't take much time. Even if you do it with a hand calculator, it doesn't take much time to do it. So that's okay. Um, it doesn't really matter if you need to do a lot of iterations to find a good approximation. But if the function is very expensive to calculate, like some absurd, super complicated problem, it takes 1 hour to calculate the function, then reducing the number of iterations is going to be important. But let's address the first issue first. First, that is what how can things go wrong? So here I'm using a different function. It doesn't matter what it is. It matters a lot actually, but I'm going to leave this hanging for a second, and I'm going to do the same exact thing. I have my f of x. I'm going to define it with a new f2. I don't remember what it is. Somebody's giving me a black box that spits out numbers, and I'm start with x1 and x2. Um, actually, well, I'll just follow it. And then I'm going to follow the same procedure. So this is the same exact code. I copied and pasted everything. I just changed the first line here, where I said f of x is equal to f2 and not f whatever it was. And then, same instructions, find root, blah, blah, blah. You may be seeing here what is happening. That is my function. Okay, start from 1 and 2. These are my first two approximations. Okay, 1.5. This is my second. So 1.5 is the approximation. 14 is the value of the function. If I do one more iteration, I change the second one. It goes now to -5. Then I change the second one again. It's -18, and I keep going. By iteration 10, my function is 2000 on the positive side and -2000 on the negative side. You you all see what went wrong, I hope. Is there anybody that's not immediately saying yes, of course? It's okay. There's nothing shameful. All right, so you all see it. The problem is that this is all nice and true and great as long as my function is continuous. So calculus 1 theorem, if f of x is continuous and f of x1 is equal to a and f of x2 is equal to b, is going to assume all the values between a and b between the points x1 and x2. But if f is not continuous and x1 is a and x2 is b, there is no guarantee that any value between um, between a and b will be assumed in that interval x1 to x2. And in fact, what is happening here is that the tangent of x is discontinuous, goes to infinity at pi over 2, which is actually what this is converging to. And so my algorithm is saying, well, the function is negative here, it's positive there. I'm for sure there's going to be a root in between. And that's something the algorithm cannot check. So that's up to you. You have to be mindful of doing this correctly. But I also want to emphasize another point here. Here I'm using the built-in function in Mathematica that's going to find the zero of a root if I give it 1 point or 2 points as an initial guess. So here I'm getting like a warning. It's telling me, well, the root, I found 2 points that bracket the root very closely, but somehow the value of the function is not going down as quickly as I expect. So that's that's a sign of something may go wrong. But Mathematica, this built-in function still thinks that this is the root. Thinks, no matter of figuratively speaking. That is to stress, and I cannot stress this enough. All of the things that we're going to see here are foundational. We're going to learn how to do these things, how to use them, and so on. You're going to find better implementations, better algorithms, better programs, and things that are already built in. You could find a library in Python. If it's MATLAB or Mathematica, they're going to have their all built-in functions. If you're not very clear on what they're doing, even if you didn't write the code, you understand the logic behind what they're doing, you may get wrong results. And you may go to your advisor and say, well, here I found the solution to this problem, use it by using whatever. And then you look together, how do you do it? Well, just put it in this function, this is what is spit out. And maybe what is spit out is actually not what you're looking for because you didn't use it right. So please, please, please be careful on how you use these things. And in fact, now if I do the plot, this stuff again, you see that the two values of x are converging to pi over 2. They're getting closer and closer, but the values of the function are blowing up. Okay, so let me stop sharing from here. And maybe I'll get off full screen. And let me start sharing from here again. Let me in a second. Okay, I'm sharing the screen. Oh, all right. So we've talked a little bit about the one of the issues you can have with bisection, that is you forget to check or you mess up and you start with a function that is not continuous. And by the way, um, function we use, the tangent, actually uh, has an asymptote that pi over 2 goes to plus or minus infinity. But that's not necessary. The function may just be discontinuous and jump from minus 0.5 to plus 0.5 for whatever reason. Um, you're still going to have the same problem. You're not going to be able to find a zero. Let's see. Mm. Now let's talk a little bit about the other problem. Um, that is the fact that the bisection method converges slowly. Um, but before I do that, it, it maybe so there are a few things, a few more things to keep in mind with the bisection method. Might as well bring them up here because they can apply in general. One is let's say you do your bracketing and you find remember how to access. This thing just says okay. Um, so I'm going to have f x x, and maybe my function does something like this. And I start from x1 and x2. Clearly, f of x1 is negative, f of x2 is positive, so there is going to be a zero in between. That's true. There's more than one. That can happen. Well, of course, you're going to have an odd number, but you may have an infinite number of zeros in between. Um, well, bisection is going to find one of them, and only one, but it is going to find one. So it may be that in the first iteration, you get, I don't know, the point is going to be something like here. So it's going to say, well, it's a positive value. So I take this as x3, and then you're going to find the solution on the left. Or maybe, the first point is here, then I'm going to find the solution on the right or whatever. But you're going to find it. Okay. The other thing that I want to point out about the bisection method that is related to the slowness of convergence is the following. Should I type? Yeah, maybe it's perfect. Okay, let's try typing. I mean, there's nothing too clever, but I don't know how to do a table here. Go away. Insert. Should be a way to do a table. No. All right. I'll just type. Um, so say we have x1. Ah, I hate this. Hold. Why? I don't want a dot there, and there is no way to turn them off. It's just so annoying. Sorry. What I ask you to do? Okay. Let's say we have x1, x2, f of x1, f of x2, and we do our table like we did before, and we have something like this. Okay, now just um, let's suppose we do as we did before. I think with Microsoft, it's one of my least favorite thing to do. So my function is going to be, sorry, one, so the points are 1 and 2, let's say, and my function in point 1 is, let's say positive, let's say negative, -1, and my function in point 2 is, say, positive, and it's 0.0001. So, uh, don't know if it's, let's see, it's taking a minute to sync as usual. So the point, I'm trying to, maybe I should, okay, let's do it this way. All right. So what the the bisection method will say here is, well, I see in the function is positive in point 2, it's negative in point 1. Um, definitely there is going to be a 0 in between, and my best guess is going to be right in the middle. But if I did something like a guess of what this function may look like, so I see it's -1 here at 1, and here I have point 2, so this are going to be x1, and here is going to be x2. My function probably looks, oops, something like this. Just looking at the values, um, f of x2 is much smaller than f of x1 in absolute value. So it makes me think if the function is reasonably smooth, probably x2 is much closer to the correct solution, so to the point where the function goes to 0 than x1. But this is information that I'm throwing away with the bisection method. I calculate the value of the function, and I don't take the value, I take only the sign. However, I could take the whole value and sorry, since I calculate the values, I could take the values and I could do um, try to do something with those numbers. And one idea is to say, well, let me. I don't know what the shape of the function is, but I can guess maybe just draw a straight line between the points x1 and x2 and the values of the function and approximate the function um, with a straight line. Here's what I'm saying. Um, I'm going to assume that the function is linear between these 2 points. And then I'm going to find the zero of the linear function. That's going to be a lot easier than finding the zero of the original function. In other words, I'm going to assume that f of x is equal to a times x plus b, and f of x is going to be equal to 0 for x equal to minus b over a. Okay, now maybe better if I share from here, because I see we're having sync problems. So, okay, share screen. Okay, so that's what I'm going to do, and it doesn't really look like a B, but I promise it's a B. Okay, now the question is how do I write um, this function? Well, okay, it's more than one question. The first one is how do I write this function? I have it written somewhere. I don't see it in front of me, so let's just figure it out. So I'm going to call this y1 as I did in the other algorithm, or if you prefer, you can call it f1, but let me just use y. So I'm saying that a times x1 plus b is equal to y1, and a times x2 plus b is equal to y2. A bunch of ways I can do it. Does anybody want to tell me what it turns out to be? Or we can use mathematics. No, I can just do it. How hard can it be? So one way I can do it is to say that f of x is equal to y1 plus some coefficient times x minus x1. So for x equal to x1, that gives me y1. So that f of x2 is equal to y1 plus c times x2 minus x1. If it's readable, x2 minus x1. Okay. And is equal to y2. So that c is equal to y2 minus y1 divided by x2 minus, which of course I could have remembered, but why remember anything if I can figure it out in one moment? Okay, so f of x is equal to y1 plus y2 minus over x2 minus x1 times x minus x1. And then I set this equal to 0. So I don't know if it's worth spending all the time writing down the details. So not somewhere else. Y2 minus y1 divided by x2 minus x1 times x. Solve for x. I don't think you need me to do it, but all right. x is equal to x1 minus y1 divided by c. Okay. Um, everybody still with me? And when I hear no answers, I never know. It's like everybody's completely lost. Uh, we got this. Okay. So I spent just a minute to write an algorithm. It's not the important thing to learn. You know how to do this. Um, you will hopefully find in physics that a lot of this useless stuff that we learn in calculus one or even earlier, or in physics one or whatever, sometimes it turns up, and it's good to remember how to do it. Okay, now how do we proceed? We started. I assumed we started from a bracketed interval, meaning that we had an x1 and x2 that bracket the root. Now we find a new point. This is going to be x3. So what what do I do now with x3? Well, I go calculate. Well, I can do actually two things, and these are in fact two separate methods. Um, yeah, uh, to hope that it will appear shortly. Yeah, okay, fine. Um, okay, two different methods, but very closely related. What is called the second method and what is called the regular falsi method or false position. So they both do what we just discussed in the same exact way up to this point. Well, almost. But let's say that if we have two starting points, bracket the root, we feed them to either algorithm, they're going to do the same exact thing and to calculate a new point x3. Now, the difference is at this point, we have two options. One, we keep the bracketing, meaning we calculate f of x3, we check the sign, and we replace whichever of the two, x1 or x2, of the points that had the same sign. And um, The second method instead is going to say let's throw away the oldest point. Now the first iteration is kind of arbitrary, which one you throw away, because they're equally old. But let's say I'm always going to throw away x1. So I'm going to say, well, now I had x1, x2, I calculate an x3, x2 becomes the new x1, x3 becomes the new x2, and I repeat the algorithm. That's what the second method will do. The false position or regular falsi, which is kind of false position, position not as in location, but in assumption in Latin. We'll just say, well, let me not take any chances. Let me make sure that I always keep the correct value between my 2 points, x1 and x2. You may, hopefully, you will wonder why we have these two options. There is, let's see, this took a lot longer than I thought. Thought we'll just blaze through this. Okay, I guess I move slower when when I can't speak or something like that. Um, there is one. There are good reasons to do one thing or the other, to do either. Let's see the first one. I throw away the oldest point. Well, what can happen, and we'll see an example maybe today, maybe next time, is that as you do this bracketing, you do if you use the opposite approach, you kept the bracketing, only one of the points moves, and the other one is always stuck. It may happen like um, in the somewhere here. Here in my little table that I do 5 iterations, and x2 never changes because it's already so close to the root. And so that's one thing. The other thing that can happen is that if the function is not well behaved, um, well, not well behaved is it's very arbitrary in this case, but if the function is not terribly smooth, it may happen that if I let go of the bracketing and try to update the points, always keeping the newest 2 points, my my straight line that I draw through the 2 points somehow moves away from the root. In other words, the of the two, if I keep the bracketing, false position, that's guaranteed to converge for the same reason as before. Because you never throw away the interval, and if the function is continuous, same catch as before, it must assume all the values between the positive one and the negative one that you have in your bracket. So the other one may fail, but in some cases will converge faster, meaning you need fewer iterations. So again, one more case where there are pros and cons to different methods. There is no one way to find the root of a function. We're going to see some more. And if you do or do not know what you're doing, what the method that you're using is doing, you may have different outcomes. if you're clear on how the method is working, this method is going to work well for my problem. So that's what the one I'm going to pick. But there are some methods that are pretty robust, a little more complicated. We'll get to those maybe next class. And those are kind of the default. And if I don't have any good reason to do anything else, this one is going to work. But they may not always be the most efficient ones for your problem, and they may not necessarily be that easy to write down. So we have only a couple of minutes left. So let me do it this way. Which button I have to push here? I'm sharing my screen, yeah. Okay. Just one more thing in the couple of minutes we have left, and then we'll see the examples. But here's how this works. Should be straight lines. Speaking. No, not what I meant to do, but can we do? Okay, red line. And be that way. And then let me take different color. I'm going to use red and green. Is there anybody that's colorblind? Is there going to be a problem for anyone? I mean, I don't know if I can ask. I think it's okay. Tell me if you don't like me using red and green. All right. Using this method, that's what we replace f of x with. And as you can see, it's the line that crosses the function. That's why it's called the second method. So it's simple geometrical construction, and we'll pick it up from here next time. But one thing I'll just throw out now is the limit of the second when x1 and x2 are very close is going to be the derivative of the function. So that may be another idea to use. And in fact, it is. We'll see it next, I guess, next recorded class. Thank you, everybody, for switching plans at the last minute. I hope the semester is going to get better than it is. We didn't start well. But one more class with the doctor appointment on Tuesday, and hopefully we'll have a few weeks of peace. Write on Canvas if you have any questions, any doubts, or if you need anything. And if not, I will post a lecture for you before Tuesday, and I will see you in person in a week from today. Thank you, everybody. Bye.
Thank you.
Sounds good. Thank you.